which one oh, okay, thank you. Yeah, so in part one, the context of generalizing exponential family has been touched upon, and the rho tau embedding has been explained. So in the whole remaining of the talk here, rho and tau are two given strictly increasing functions, and we assume them to be continuous and sometimes even a little bit more technical assumptions. In this second part, I will comment further on the metric tensor, which is the local property in the statistical manifold, and also on the geodesics determined by a connection, which is then a global property. And the point of view that we take is that if a metric is given, only one function has been determined, and in the rho tau formalism there is still some freedom left, which you can make use of to change the geometry of your manifold without changing the metric tensor. And that's what we call a gauge freedom. You are free to choose, under certain limitations, a connection without changing that metric tensor. And for example, you can pose yourself the question, is it always possible to choose for a flat geometry? And the answer is negative. So that's one thing I will come back upon. I have still 9 remaining transparencies, sheets. Each of them has a title, and you will see, so I hope I will not run out of time. Statistical models, okay, the importance is quite clear. So I will not say much about this. The metric tensor, so I now start from the rho tau divergence formula, which is written here in a form which I like quite much, because the essential properties of a divergence function can be read off from this expression. X is the underlying measure space, P and Q are two probability distributions, and the integration here, V is just a real number. The integration is a Stieltjes integral involving the rho function, while the tau function here is used as an argument, and you integrate from the one value of one probability distribution to the value of the other one. Why is this an interesting way of formulating? If you can work it out, of course, and it's the same as the one showed in the previous talk. But you can, for example, see that if Q equals P, then the integration will give you 0. While otherwise, because tau is an increasing function, you can immediately see that the result is always either 0 or positive, and so on. So the essential properties of the divergence you can derive from this expression. And then you can derive the rho tau metric tensor by taking twice the derivative with respect to the second argument. Okay. Derivatives with respect to the parameters θ1 up to θn. Okay. And the result of that calculation, starting from this formula, it gives the one which John has shown already, which is a very symmetric expression, integration over the measure space of the first derivatives of the rho embedding and the tau embedding. And the important point also we heard already is that it's symmetric under exchange of rho and tau. But in fact, it depends on only one single function. Yeah, you can see, of course, the essential properties, covariance, invariance under exchange of rho and tau, and positive definite. It depends on a single function phi, which is 1 over rho prime tau prime, okay? Which is the basis of what we call the gauge freedom. We can now keep this function constant and change either rho or tau or both, but keeping the function constant so that the metric tensor does not modify. Let me now say something about tangent vectors. The metric tensor is symmetric under exchange of rho and tau, but we have to break that symmetry to go on. And the choice we make is to use the tau embedding to define a random variable x, and to use the rho later on to define expectation values. So we give a different meaning to the two functions, although in principle they are quite equivalent. Okay? So we have a random variable x, and we then introduce a bilinear form, which is written here, and which also breaks that symmetry. It's rho prime divided by tau prime. Okay? And it's chosen in such a way that the metric tensor becomes that inner product, or scalar product, inner product, between the derivatives of that random variable x. So you can realize now a tangent plane. Well, in the first place it will be a finite dimensional Hilbert space where the unit vectors are the first derivatives of that random variable. Okay? And then the point is that we consider this linear space as the tangent plane to the rho embedding of the family. And the reason to do that is that for an arbitrary random variable, if you calculate the derivative of what's written here, that's essentially the unnormalized expectation of that random variable u with respect to the rho embedding. If you take the derivative of the expectation, then you get a very simple expression, which is the inner product with the unit vectors in that tangent plane. That's the reason why we have that geometrical interpretation of those derivatives as being the unit vectors in the tangent plane at a given point theta. Then in the paper we formulate some equivalent conditions for the metric tensor to be Hessian. By definition that means that it's the Hessian of some potential phi. And the 6 conditions here, I have written them in a very symmetric or systematic manner. This first line here, as we saw before, is the metric tensor. Okay? And the metric tensor is then the second derivative of the potential. If it's Hessian, there exists such a potential. But what we now can do is move one of the derivatives to the other function, either to the rho or to the tau. Okay? Then you have two different quantities, which are not necessarily metric tensors. But again, equivalent condition is that there exists a potential such that the expression in the right-hand side is the Hessian of that potential. Okay? So in that way we get 3 equivalent statements. And of course, if you have a potential, then you also have dual coordinates, which are the first derivatives. And that gives the 3 remaining lines here. The eta I, or the, I would say, standard dual coordinates of the theta I, the parameters of the model. And it's enough that such coordinates exist such that the derivatives give me the metric tensor. And that again I have Hessian metric. Okay? And the same for the 2 other coordinates, which you can define in a similar way. Okay? So that's a rather abstract theorem about when the model will have a Hessian metric or not. Okay, let me now go, and I have to look to the time also. Tau connections, they were introduced in the paper of the 7th of June in 2004. as a generalization of our various alpha connections. They are clearly symmetric by exchange of rho and tau, except that alpha goes to minus alpha. Okay? Because the first line goes to the second line, I have to change the sign of alpha. So that's a very elegant definition. It depends, of course, on both tau and rho in a way which is almost symmetric, but you have to change alpha. Okay? And from the definition of dual connections, you can immediately see that the minus alpha connection is the dual of the plus alpha one. Okay? That's almost the definition which stands there. Okay, now shortly something about flat geometries. It's some calculation to see that the minus one rho tau connection will be identically zero if, and now I use my notation of tangent plane, if the second derivative is orthogonal to the tangent plane itself. Okay? That's a quite natural condition, and it is precisely expressing that the minus one connection is identically zero, which means that the geometry is a flat one. Okay? And so that gives me the proposition then, because it's known that if a connection vanishes, if one of the dual connections is flat and the other one is also flat, so if gamma minus 1 vanishes, then the gamma plus 1 is a non-trivial flat geometry for the statistical manifolds. Okay? And so star alpha minus 1 is flat, but alpha equal plus 1 is then flat as well. So the theta I, the dual coordinates, are affine coordinates in that case. And what we can prove is that then the rho tau metric is Hessian. Okay? And if it's Hessian, then immediately that says, so when there's a flat geometry, alpha minus 1 vanishing, automatically it's a Hessian metric, which means that if my metric is not Hessian, then you cannot find a flat geometry. Turning the theorem or the statement in the other way. Then very shortly, I think I have to hurry up. Right? And about phi exponential families, definition here. So the exponential function is replaced by a deformed one. And the result here is that the rho tau, that is the metric which I introduced in 2004, is essentially the same as the rho tau metric, provided that the function phi used in the definition of the phi exponential family is exactly that 1 over rho prime tau prime which we saw before. Okay. And also for that kind of model always dual coordinates exist, and in particular then the theorem says that the metric is a Hessian one. So what can we do with this? We can conclude that for any arbitrary pair of rho and tau, there are always models for which the rho tau metric is Hessian, because you can define phi to be this 1 over rho prime tau prime, and then you can introduce those phi exponential families, and they have automatically a Hessian metric. That gives a lot of freedom of pairs of rho taus, which, if you want, can be made, can be provided of a Hessian metric. So the summary is just what I said, and I will stop here.
Any questions?
Is there some work on the quantum setting?
Quantum setting.
Yeah. There is work on the quantum setting, and the problem, still open problem in the quantum setting, is not for the standard case, but for the deformed exponential functions. There's still There are some results, but it's clearly not a finished thing.
You will.
I'm sorry?
You will.
You will finish.
You.
You will finish.
I'm working on that.
Yeah. Next time.